When someone says the word robot, this is probably what pops into your head. Or maybe you are thinking of this guy, a superhero who dances better than most humans, also very cool, also not this. Real robots don't have arc reactors or six pack abs. They are arms in factory, wheels in warehouse, or a arm doing surgery with more precision than any human hand. Today we are breaking down the actual anatomy of robot, how we classify them, and the math that lets them move exactly where we want, kinematics. Let's get into it. Think of a robot the same way you think of your own body. You got bones, joints, muscles, your brain, and senses. Your robot has the exact same five things, just with different names. So links are the skeleton, joints are where it bends, actuators are the muscles, sensors are the senses, the end effector is the hand, and the controller is the brain. That's the entire anatomy of robot. Robot classification. There's a second simpler way to classify robots too by generation based on intelligence. First generation robots just repeat a fixed programmed motion with no feedback. Second generation robots use sensors to adjust like a robot, and that's stops if it senses an obstacle. And third generation robots use AI to learn and make decisions on their own. So classification isn't just about the arm's shape, it's all about how smart the robot is. Robot kinematics. Now, for the part that actually makes a robot useful, kinematics. This is simply the study of motion, how the joints of robot relate to where its hand ends up in space. There are two directions to this problem, and here's the simplest analogy I can give you. Imagine you want to pick up a cup of coffee on your desk. Your brain doesn't consciously calculate each joint angle, but robot has to, and it can approach this is in two opposite ways. Forward kinematics. Forward kinematics asks, if I know the angle of every joint, where does the hand end up? It's like saying my shoulder is bent 30 degrees, my elbow 45 degree. Inverse kinematics. Inverse kinematics is the opposite, and it's the harder problem. Here you say, I want my hand at this exact point, the coffee cup. What angle do my shoulder and elbow need to be? You are going from position, joint angles. This is what a robot controller actually needs to solve millions of times. Because when we program a robot, we care about where the end effector goes, not what each individual joint angle is. The tricky part with inverse kinematics is that there can be more than one solution. The summarize forward kinematics angles in, position out, one guaranteed answer. Inverse kinematics position in, angles out, sometimes multiple possible answers, and it's computationally much harder. Nearly every robotic arm motion you have seen ever. Real world's motion, that's robotics, not science fiction, just very elegant engineering.